Okay, let's make a start. So hello everyone, I'm Giuseppe from Evolution AI and I'd like to welcome you all to the virtual London Machine Learning Meetup. So today we have Manzil Zaheer from Google, who's going to talk to us about the BigBird. The talk will be followed by a Q&A session that will be moderated by Sinead Williamson from the University of Austin, Texas. So a little bit of housekeeping as usual. So you can ask questions about the talk at any time by using the QA function. So please use the QA function rather than the chat, as that makes it easier for us. And during the QA session, we will go through all the questions. I mean, we'll try to go through all the questions, and we will allow people to ask the questions. So if you guys want to ask the question yourself, please raise your hand and we will unmute you so that you can ask the question and have a short discussion. Okay. So if you need anything during the talk, you can use the chat to speak to the panelists. And finally, the talk is going to be recorded and will be made available on the Meetup's YouTube channel. So without further ado, I'll leave the stage to Manzil. Enjoy the talk.
Thanks for the invitation to talk. Today, I'm very excited to talk about our work on scaling up transformers to longer sequences, which not only achieves like state-of-the-art results on many tasks, but also we could provide some theoretical guarantees on its performance. So let's get to it. As we all know, transformers have revolutionized the field of NLP, right? It's getting used from everything, right? From translation, summarization, question answering, and almost anything we think about in NLP. Also, it has gaining popularity in image, speech, and other related fields. And recently, people have generated interest in computational biology in tasks like protein folding also. So in this talk, what I will do is I'll first try to give some like motivation and background on what transformers are, what our proposed method is able to solve some of the bottlenecks of standard transformers, and then finally some experimental results on it. So just to recap, and many of you may already know that transformers are simply like a sequence to sequence model. What it means is that the input to a transformer is a sequence of tokens or a sequence of vectors, and output side is also another sequence. And this transformer model itself is composed of many repeating layers. So it's the same layers repeated many times. And if we look at what this one layer has, so this one layer has basically two components. It has a feed forward layer, which kinds of transforms each token's embedding to a different space. But it also introduced this novel mechanism of self-attention. And the self-attention applies on the whole sequence, and output is another sequence. And let's go into like slightly more detail of what is behind this powerful attention mechanism. So attention or self-attention is a mechanism in which like you have a source sequence from which you would attend on a target to sequence. And in case of self-attention, this from and to sequence are the same sequence itself. So what you do, the first step is you try to build some intermediate sequences from the source and target sequences. So in case you build a query, key, and a value sequence. So from the from sequence, you make a query, and from the target or to sequence, you build the key and value matrix. And now you want to like attend from each token in the from sequence to each token in the to sequence, right? And for this, you have to do this like kind of quadratic computation. So for every pair, you are trying to compute this compatibility score or the attention score. And once we computed this whole n by m attention score, you do a weighted average with the value, and you finally get the output. And this can be compactly represented as this mathematical statement also. But so this diagram is somewhat like complicated, but the main thing I want you to take out of it is this attention score computation is a quadratic computation, which is why this attention mechanism is very expensive. So in particular, like imagine what was there before transformers, right? We had RNNs, we had convolutional neural networks doing text classification or other tasks in NLP. And notice for each of them, the cost both in compute and in memory was linear in the sequence length. Whereas once this transformers came in, it became like quadratic both in memory and operations compute, as I explained in the previous slide. So even in case of like compute, if it's quadratic, maybe we can somewhat like have a slower output, but we can still compute. But if our memory is growing too much, but we have like GPUs and TPUs, which have like finite memories, right? They have like 16 GB or 32 GB in some newer ones. But once you have that fixed memory, and if your model needs a larger memory requirement, it just won't work. So this becomes like a very essential bottleneck, that we have to reduce this memory requirement to be just able to run on tasks which require longer sequences. And this is like a well-studied problem. Like since transformers are so powerful, many people have tried to scale up transformers to longer sequences. And there have been many attempts. So there was a recent paper at ICLR this year where they try to like organize these different long range transformers and try to compare them systematically. So they tried to come up with a benchmark 6 tasks. So which they call LRA score, and higher it is better, and it shows if the transformer is more expressive. And then there is also the axis of like memory consumption, like how much memory this approach takes. And what you ideally want is to be in the top right corner, right? Highest performance with the lowest possible memory consumption. So you can see like the standard transformer is very good in the performance axis, but takes a lot of memory. And whereas these many other works which are trying to speed up or scale up transformer to longer sequences are like very fast and memory efficient, but they lose in the performance axis. Like there is a gap from transformer. And that's like the main punchline of basically our work, is we are trying to be able to get a good trade-off in the memory and the expressive power. So we are reducing the memory consumption a lot, whereas not sacrificing the performance. So I'll just like go next into some of the ideas, like basic ideas, which some of these methods like linear transformers have been using to scale up, and then we'll go eventually to our proposed method. So what is being done in works like linear transformer or linformers, they're seeing this attention as this matrix operation written, and they're trying to approximate this to speed up. So as you can imagine, like what can be a first approximation you can think about doing speeding up this operation? So one can imagine, maybe what if I try removing this nonlinearity, right? There's the softmax nonlinearity, let's drop it. So if you drop that, something interesting happens. So we know that matrix multiplications are commutative. So we can just like, instead of computing query key first, we can try to compute key value first, and then that reduces the compute requirement and also memory and everything from quadratic to linear. So that's very good. But this dropping of this nonlinearity comes to us at a cost, that it reduces the expressive power. As we know, like in neural networks, every time you add more nonlinearity, everything, the errors goes down and we do better. And by removing this nonlinearity, as expected, it will do worse. So for example, in their original paper, they were trying it on speech recognition task. And you can see the speed up, like in the time, it reduced the time by more than 3x. So that's like very massive reduction in time, but they had to suffer a cost, that the phoneme error rate increased from 5 to 8. And that's like somewhat significant in speech domain. So then people were asking like, okay, can we bring back some amount of nonlinearity, right? Without maybe sacrificing the linear speed up we got. Can we try to do some amount of nonlinearity back in the picture? So maybe not a full softmax, but can we do something else? So then the idea came that, okay, what if we use the kernel trick? And this was the idea introduced by the performer paper, where they were saying, instead of softmax, let's use a kernel function here. Once you have a kernel function, you know it can be factorized. So you can just like factorize it as its component mapping functions. And once you make this mapping, then again, the matrix commutativity trick applies and you can speed up. So what happens when you try to do like this? So it improves the expressive power somewhat. So clearly from linear transformers, you go up. But still there is like a big gap in like this LRS score from the transformers. So there's still a lot of way to go. And that like basically brings us to our proposed method, which is trying to bridge this gap. And the way we are going to bridge this gap is we're going to look at this whole attention mechanism from a different angle. So instead of looking at it as a matrix computation speed up, we will try to look at it as a graph. So what does that mean? So let's again look at the self-attention, right? So input is a sequence, and you want to like compute this attention score over all words. So what we can think is maybe we can view this as a fully connected graph, and the edge weights are equal to the attention score. So this dense matrix can be represented by this fully connected graph with the edge weights. So then the question comes like, some like very basic questions we can think about, like if we have this complete graph, do we actually need all these edges? Can we get rid of some edges? Or even what is the source of this edges? Like why was it needed in first case? So some maybe intuitive arguments can be that there are like the edges might be doing like co-reference resolution, right? There were it and other words you're trying to see who's related to which word. And there may be also like you want to have some interaction between the subject object pairs. So all those kind of information needs to flow between different words. And that's what this fully connected graph is providing, a very easy way to information to flow between different tokens. And if you are familiar with like graph theory, there is this concept of mixing time, which kind of measures this, like how easily can the information flow and how fast. And in graph theory, we know that fully connected graph is not the only graph which has like low mixing time. There are many random graph models which have a very small mixing time and only has a linear number of edges. So that became like a very interesting idea to us, that can we maybe use a random graph like Ardashrini or Watt-Strogatz and replace with the complete graph, and maybe because it has a very low mixing time, it may work just as well as the original full attention. And in particular, we will like focus on this Watt-Strogatz kind of graph model because it has some like nice properties which resonates with a NLP domain. For example, when you try to construct a Watt-Strogatz graph, what happens is you start with a d-regular graph, right? So what that means is each node is connected to d minus one other nodes. And so you can think of that as being like the locality, right? Each token is connected to its neighboring d tokens. And then what you add on top of it is some random edges between different nodes. And this can be like thought of like some random attention happening between two pairs of tokens. So then we said, okay, let's take this attention mask and apply it on standard tasks for which like transformers are used. So for example, take BERT kind of task, apply it to some simple question answering, some simple entailment kind of task. So here I'm representing like a BERT base, which has the full attention mechanism and its performance on like masked LM, question answering, and NLI tasks. And I'm also like saying, okay, what happens if we only put that random mask there? We put only the local window pattern, or we do this combination of random plus window. So we can see that it definitely does, this combination of random plus window does better than each of them, but still there is a gap compared to the original BERT, right? Like this gap in squad of 3 points or in natural language inference of 3 points is definitely not good enough. So there's still something missing. So so we try to understand like why is this gap happening. And what we did was we tried to look at the proofs of standard transformers. Why are they like so powerful and universal approximation? And from there, we saw that there's a requirement of some nodes to have like a global connection. It needs to be connected to everyone for that universal approximation proof to go through. So from that motivation, we inserted a few global tokens. So some of the tokens we said were just at the start, which can like attend to every other tokens in the sequence. So now this means our full attention has basically three parts. It has this global part, it has the locality windowed part, and it has these random attention part. And now you can see like this new row added in our previous table. And this new row is like very, very competitive with the full attention while being only linear in number of compute or memory requirements. So that seemed like very promising task. And now, like, since we now have like a very good mask, we are trying to say, okay, did we lose any property by going down to linear, right? Are we still universal approximator? Are we still Turing complete and so on? Like the all nice known properties about transformers. We are trying to see, is it applicable to our sparse transformer? And we found that you can actually prove that our sparse transformer is also still maintains the universal approximation property and is also Turing complete. And I'm just going to give like a very high level picture of what we are doing to show these kind of properties. So in like a universal approximation kind of property, what happens is you try to show that a given input sequence mapped by a target function f is you can like reconstruct this to some arbitrary approximation epsilon, and we have to show that this is possible by our like sparse transformer. So the idea which you are trying to do was we will discretize this original input sequence, and once you have discretized it, we want to like encode it as a sequence of single scalars and then use the standard universal approximation properties of feed forward layers. So the reason why discretization kind of works is because we are assuming the input domain, the functions mapping is it's like a continuous function, right? So you can always like discretize it within some error epsilon on a grid, and then reconstruct back, and your overall loss will remain to be epsilon. So this is like the whole pipeline which we will try to use. And then the challenge remains in how do we show that there exists a unique encoding of this discretized vector so that we can invoke the standard universal approximation properties of feed forward layers. And the main thing to notice there is that you can't like just do individually on each vector map encoding, because the output of the same vector, like say this green vector, in two different contexts can be different outputs. So here it became something else, and here given a different context, it became a different vector. So this encoding somehow must capture both this vector, like each individual vector, as well as its context. And it was somewhat like a technical design, but we could come up with a selective shift operator and requirement of like one global token which talks to everyone else, such that we can achieve this unique encoding. And since there is only like one global token and nothing else, our overall map is still like linear in sequence length. So for like we could like write this down as a theorem statement also, that given any function f and some epsilon error bound which you want to tolerate, there is like a sparse attention graph defined by our like BigBird architecture, such that our distance from the true function will be bounded by epsilon, will be less than epsilon, and this distance is like an LP metric, so it's way more powerful than just a point-wise approximation. And but all this like power doesn't come for free. There is like a limitation. Like what can happen is now we might need more number of layers to perform the task. So for example, there is this task where you want to compute the furthest vectors in a given set of vectors. So you are given n vectors and you want to find the one which are pairs of one which are furthest from each other. So if you had like a standard transformer where you are doing like all attention, like full attention, this becomes like a trivial task, right? You take the inner product and you know which one has the maximum one. Everyone picks the maximum one. So you can achieve this in like one layer. Whereas if you are trying to do anything with sparse transformer, not just BigBird, like any sparse transformer, it's like we show that you will need at least n layers. Like any sparse transformer having a linear number of connections, there's no way you can do it in less than n layers. So that's like somewhat a limitation. But again, this is like a very worst case limitation. In practice, maybe these kind of tasks never show up, as we will show with our like empirical results. Also, having these nice theoretical properties is not enough, right? We want to be able to implement it and work on real world data set and scale. So what's the problem with these kind of like sparse attentions we have showed? The problem is that our modern machines like GPUs and TPUs where we run are like these single instruction, multiple data kind of devices, right? Where same instruction needs to run on all data points. So matrix operations are like amazing, but anything these like sparse matrices or sparse operations will require like gathers and so on, which are very slow and expensive, not very good. So we tried to, we came up with this trick of blockifying, which allows us not to use sparse ops or like use very minimal amount of sparse op while still being able to achieve this sparse, like these are like target BigBird attention pattern. So the main thing is we, instead of doing random attention individually of each token, we always do everything at block level. So to give like further intuition, what I will do is like say, just recall what is happening in full attention is you have this sequence of query vectors, sequence of key vectors, and I'm just coloring them to guide us to understand what's going on. And you want to do like a matrix product between them, right? So you achieve this full n by n matrix where like green times this shade means your product here and so on. And now suppose I will do the following thing. So I will instead like blockify and reshape that matrix into a tensor. So I reshape it as this 3D tensor and now do a tensor, dense tensor multiplication. So no sparse op. And what you recover is this diagonal part of the attention pattern. So the block diagonal part of the attention pattern is there, but that's not enough. So just having this diagonal is not enough. So then what you can do is try to make some copies. So you take this key, make a copy, and then roll it to the left and one to the right. And then again, do the same thing. We'll reshape into a 3D tensor and do dense matrix multiplication. So now if you do this dense matrix multiplication, what you'll recover is along with the diagonal, you'll recover one off diagonal and another off diagonal. So that means we are at least covering plus W and minus W from each one on the diagonal. So our like locality pattern is kind of covered. So we have this whole locality implemented this way without doing any sparse operations. So just, yep, so this way. And once we have this, then the what is left is to add the random components. To add the random components, we don't have much option but to use gathers. And since these are like only a small number of random blocks, so that reduces the number of gathers also. But we get these random edges in here. So overall, what happens is we have the query vector. We also have this key matrix being transformed to this dense vector. So we can pack all of this into a dense tensor. Right? There is a key for this global part. There is this windowed by rolling and copying, which we got. And then there is this random things which obtained by the gather. But all of this is packed into a dense key tensor, and then you do the tensor matrix multiplication to achieve this sparse pattern. So kind of without any sparse ops, we are all getting this sparse pattern. So this is very efficient on GPUs and TPUs. So the just to recall, like what happened was we could like show a very efficient implementation for a transformer, which is like almost as expressive as the full transformer in theory, as well as like some benchmark empirical data sets. So now I like move on to some of the actual experiments we did. So first, we like in any NLP task, we have to like pre-train it using masked LM task. So nothing interesting there. We pre-trained our BigBird model with it. Then we tried to apply it for question answering and summarization, kind of like generative tasks as well. So let's get into it. So for question answering, what happens is usually most of the state-of-the-art methods operate in two stages. So given a question like how many of Warsaw's inhabitants spoke Polish, what you will do first is try to retrieve what are the paragraphs where this question may be present. So it may be present in the Polish language article or the article about Warsaw, or just maybe in the article about 1933. Right? You may retrieve these. And then once these articles are retrieved, you give it to a machine comprehension model, which is usually BERT or some transformer, which will like select the span of the answer and give out the answer. So what is the bottleneck here? So bottleneck here is having like retrieving the right article or the right paragraph, which has the answer is hard. So, but if you are allowed to say retrieve 10 paragraphs and say one of them will have the answer, that's much easier than being able to retrieve just one. So now the problem is if my transformer or my machine comprehension model can only read 512 tokens, then you don't have like budget to retrieve many paragraphs, right? You can only retrieve maybe 2 or 3 paragraphs. So what like this BigBird or these long range transformers enable is now you can like retrieve so many paragraphs and do question answering on a much wider number of paragraphs, which should ideally yield a better final accuracy on the question answering task. And the way you usually give these question answering input to transformer or like BigBird or most of the tasks is like standard. You take question and then concatenate it with all the other articles or paragraphs you got. And on the output side, you're trying to predict the span. So where the answer starts and where the answer ends. So that's what is the standard setup. So using this and some more tricks on regularization and so on, we were able to like achieve really state-of-the-art results or very close to state-of-the-art results on multiple benchmark data sets. So including WikiHop, Trivia QA, natural questions, Hotpot, we were getting either the best performance or being very close to the other state-of-the-art results. And notice that for all other methods are kind of like data set specific. They are just designed to work on one data set and don't actually do as well on all the data sets. Similarly, we found some like results on document classification, especially on the cases where the improvements was high when the input on the input size, the documents were longer than 512. So here excess fraction means how many of the test examples were exceeding 512. So for example, in archive, every example was bigger than 512 and you wanted to classify the categories, and you could see a big jump over Roberta. Another task where we tried to apply this was document summarization. So if you have like a long document, the important content can be not necessarily at the start of the document, right? It might be at the end or somewhere else where you made a section on conclusions and you're writing all the important stuff, right? But the if you just use a standard transformer with 512 length cutoff, you might miss this important stuff. So your summary will not be very good. And what these like long range transformers like BigBird enables us to like look at much longer context. So if you look at data sets like archive, PubMed, and so on, they could like achieve sequence lengths like usually 2000, 3000, and so on, way more than 512. But on the output side, it's very short. So what we propose is we'll try to use this sparse mechanism only on the encoder side, and on the decoder side, we will use the standard full attention. So our input would be something like, or our setup will be something like BigBird encoder, taking in the long documents. And you have cross attention from the decoder, which has a full attention and generates the small summary. So in these kind of tasks, we found that the gain in both like base size or large size, so it's not related to number of parameters. So it's the gain is coming from being able to access the long sequences, that you get like significant gains in the route scores from like state of the art Pegasus models at 43 to 55, or even at the large size, like 8-point gains, which is very significant. And just for completing the story, we were seeing like, what happens on a short sequence tasks? Does this sparsity hurt us too much? So we were trying it on the standard glue benchmark, right? The language understanding benchmark. And on all these different tasks, the performance of BigBird might not be the best, but they are like very competitive to BERT, ExcelNet, Roberta, all of which are like all this full attention mechanism transformers, and it's like very competitive to that method. And similarly, we see in the short document summarization also, where the input document is very small. So the results are like very comparable. And similarly, we had some like novel applications to genomic tasks. And since in interest of time, I will just like quickly skip over it and say that on many downstream tasks, we got like a really good performance, and I can go into more details in the question answering session if someone is interested. And so just to conclude, we propose like basically a memory efficient mechanism from which like reduce the memory cost from quadratic to linear. And this memory is the real bottleneck, right? Because without the memory, we won't be able to like just run it. And not only it got like state of the art results on various tasks, we could get like some theoretical guarantees showing its universal approximate measure. Excuse me, it's a universal approximator, and it's also Turing complete. And yeah, with that, I would like to conclude the talk. Thanks.
All right. Thank you very much for the very interesting talk, Manzil. So I now hand over to Sinead, who's going to lead the Q&A session. So if you guys have any questions, please add them to the Q&A panel at the bottom. Thank you.
Hey, so thank you. And I will default to reading your questions as you send them in. But if you want to ask them yourself, please raise your hand and I will let you speak your question. So we had a couple of questions about the fully connected layers. Both, can you elaborate a little maybe on the importance of this fully connected layer? So it seems to give an important, like I liked your intuition about how it gives you better connectivity. But for example, compared with just the wide diagonal, would you still be able to get at least the theoretical results provided you have provided you have the connected diagonal, or the fully connected rows and columns important for that?
So for any theoretical results, having this fully connected, this global token is important. So we might not need multiple tokens, but you need at least one. So without that, the theorem won't go through. So the main reason is, again, what is going to happen is you want to like be able to like distinguish the same vectors in many different contexts, right? So this vector, if suppose it resurfaces even at this position, and you want to like distinguish it from this one. So what is happening is you will like delegate this across like different layers, and you want this global attention to be able to like separate it out, like all of these vectors at this position, I'm going to put it in one bucket and move on to the next one, put it on a different bucket. And you need at least one global token to be able to do that separation. So you can see this like exact detail in the math, but yeah, there's like, it's not very easy to explain it intuitively, but that's what is going on.
Yeah. Maybe I can just add one thing, which is that this is specific to our proof, and it may be possible that you can come up with some different proof, but at least our proof really crucially uses the fact that it's a global token.
Okay, thank you. I've got a couple of questions. So from Julia Clark about the timing. So I noticed that while you have a very impressive memory speed up, the timing is much more comparable to the more traditional methods.
Yep. So I agree. So our main goal in this project or this thing was to reduce the memory consumption. So we want to able to at least run it, because time wise was not our like main concern, at least because you can just maybe, it's not taking more time than the full transformer, but still operating on much longer sequence, right? So in some sense, the time is not reduced as much. And that's one reason for that is just we want to be able to maintain this full expressive power, right, for full transformer. So our operations are more costlier than say linear transformer or performer, but the gain we are getting is in terms of accuracy. So we if you didn't have the memory reduction, we won't be able to just run it, right? We will get an out of memory error. If it's only slow, it will just take some time, but you can at least run it and get good accuracy. If you actually are like very time constrained, and then I would still like prefer like, okay, go to performer or something else which runs way faster. But if you are more it's like a trade-off, like you want to trade off it. If you are more worried about performance, then you have to somewhat sacrifice on the time and still be able to use longer sequence. And so on the standard like 16 GB GPUs, we could go all the way till like on base size, it can go all the way till 8,000 sequence length without any gradient checkpointing. And if you want to do gradient checkpointing, that further allows you to do more longer sequences.
Fantastic. Tom Dietz asking, how do you choose the sparsity? Do you have any guidelines for that? Or is it something you have to tune in your learning?
So in all of these experiments which we reported, we used the same amount of sparsity. And the way we were selecting the sparsity was making sure, so the way we selected how much sparsity will be is in each row, the total number of attention it's doing is fixed to be exactly 512. So even if the sequence length is like total 8,000, it will just attend to 512 of them. So that 512 just number came from what BERT was doing. So we just picked on that 512, and each row it's attending, total number of inner products per row is exactly 512. And for all, we didn't tune that. So all of these numbers on summarization, classification, all of them had like exactly 512.
Kind of on a related question, Kumar Sridhar asks, what in the full BigBird model is the benefit of the random tokens? Okay, so you showed that it gave better performance when you were just comparing against with the diagonal, but Kumar points out that the BigBird larger version doesn't use these random tokens, but still gives really good results. So.
Actually, so I'm confused also. So the random token is somewhat so which result is he saying about is?
So yeah, here you look at yeah, on that slide that you were on.
Yes.
Yeah, so clearly you have an improvement of the random plus window over the window. And that makes sense. You're getting sort of greater connectivity. You're going to be improving that mixing time over just having the sparsity. But it feels like once you've added those global steps, maybe you have less need for the random because you already have full connectivity through the global.
Yeah. So you have full connectivity, but so in worst case, what will going to happen is you have only the global token, right? No random ones. So the path from any two random, like if I pick some token I here, some token, maybe a graph is a better place. So yeah, if I have, so assuming there's one guy which is connected to everyone else, but if you now want to talk to anyone else, your path is always of length 2, and across multiple layers, the way you have to talk is always will like keep growing 2 times number of layer. But if you add like random connections across layers, right, in different layers, what we do is actually have different random patterns. So now in expectation, actually instead of 2, that goes down way lower because each layer will have a different random pattern. So accessing any I and j, instead of 2 times L, it's like almost L actually, or like way lower.
So if I can maybe add a little bit more, I think adding randomness helps, like it allows more pairs to talk directly or in any given layer. And it's certainly true that adding more global tokens helps, but at a certain point, we find that adding random is better than adding global for every extra one.
Yeah, it's like basically diminishing returns, right?
Yeah. So like the points we choose is that somehow we find the one that maximizes all 3.
Okay, so would it be fair to say that in your experiments where you don't include the randomization, you're in a very large setting where you can't afford the extra cost?
So we have actually, so if you think of this question answering task and long former as a baseline, so long former baseline is actually not having any random pattern at all. And it's very similar to our window plus global. So it has some like striding here and there, but other than that, it's very similar, but you do see a gap between the performance. So it definitely makes. And by the way, I'm just going to introduce, I think, so the other person answering the question is Guru Ganesh. He is a co-author on this paper.
Thank you. Thank you, both of you. So carrying on along the global tokens, Daniel Paver asked a really interesting question about what the implication is of picking the first token as the global token. Have you found that there's any variety in performance by choosing different choices? And in particular, is there any way that you could use a data-dependent decision, right? So for example, if you have some knowledge of the structure, could you use that to inform and get better results?
Yes, exactly. So that's a very good question. So for many tasks where we don't understand the structure of the problem, or like maybe say, for example, I was like a novice or like almost a newcomer to any of these computational bio tasks, right? I couldn't understand what are these structures. So there I would prefer something like a black box, right? It looks like a transformer, it will do some random things inside and it will produce good results. So that's well. But there was this another paper where people tried to use, which is where we combined it with BigBird also, where if you know some like structure in your data, you can exploit it. So that's this extended transformer construction where if you know, like in question answering, for example, you are doing this question and paragraphs, like different paragraphs, you may have already a sense of structure. Let me show you something like, okay, I'm missing that slide, but so you have a sense of structure, which allows you to maybe say all the tokens inside here, we can like attend together and have a summary token for each one of these paragraphs instead of just having global tokens here. And that does help. So that's there in this ETC paper. And for achieving like some of these state of the art, we had to actually like combine these domain knowledge in case of question answering, which is like a very competitive task of these domain structure inside selecting that sparsity or that where that global tokens are sitting. So that does help, but we don't have like an automatic method to come up with it. So in cases where we don't know any domain knowledge, I suggest to use the random tokens and where, like the first K tokens, and that works. And where you don't have, where you have some domain knowledge, maybe we can structure that global tokens according to our document or the task structures.
Fantastic. We've got a couple of questions about the genomic data, which is something that I'd also be really interested to hear about, both general, wanting to know more about the genomics, but also a couple of questions addressing the fact that genomic data tends to be much longer than human language sentences.
Yeah.
Right? So Nicolas Gontier was interested in whether the number of input tokens is still fixed, and Tom Diet extended that to like, how do you extrapolate this to such long sequences as we get in genomics?
Yeah. So there are like, I agree. So in DNA sequences, if you just look at this character or these base pairs, they are like very small, right? So we did certain tricks. So first of all, like how do you do in NLP, right? So earlier people used to do word-based boundaries and have one word as a token. But in these days, what's becoming popular is these byte pair encodings or sentence pieces. So what we did was, okay, run the same byte pair encoding on top of DNA sequences. So you already get like many of the commonly occurring DNA fragments as like one token. So in general, these byte pair encodings which we found were of length 8. So it was taking 8 base pairs at once on average. So that like already reduced from the whole DNA sequence length by 8. And the other extension which we were getting was basically using our BigBird, which was moving it from 512 transformer to 4000. And this is exactly what the longer context, these other methods like CNNs and so on couldn't look at that long window. So our transformer was able to look at 4000 times 8 kind of base pairs at once to do the classification. So I agree, like the whole human genome is like really, really long, but maybe not the whole genome is required to maybe just predict where the promoter region is and so on. So, but maybe a longer context is still helpful, and that's what we are able to see.
So do you feel like some of your improved performance is due to this ability to look at longer sequences?
Yeah, so two things. So yeah, definitely ability to look at longer sequences. And we also brought in the same idea, which got a lot of success in NLP, which is pre-training. So we also did pre-training in the same sense you do it in NLP. Like what you do is you take the entire human genome sequences, chop it, like do sentence piece, and then mask random tokens here and there, and then do the masked LM task. So given the surrounding context, try to predict what were the base pair there. So this allowed like a lot of pre-training and maybe the neural network to understand various structures inside the genome sequence. So it's very similar to how masked LM in NLP allows you like language understanding. Most likely it enabled something like that. And that combined with a longer sequence length helped us. So in the appendix of the paper also, like we had a plot of with the sequence length, how does this differ? And you can see a gap there.
Thank you. So one thing that a couple of commenters have asked about is the relationship to this concept of mixing time, right? So I really like that in the sort of motivation for using a graph that you're inspired by this idea of mixing time. Is that something that plays in explicitly to your proof, or that you can make a more concrete connection to the performance?
So one thing is that I think the mixing time certainly helps us understand why having random graphs might help. So I think one of the things is our proof is very much an existential. It's sort of a proof that these models are as expressive as the full transformer, but we didn't really try and optimize it. What I think adding more random layers will do is it'll allow you to optimize it. It'll make it easier for nodes to connect, although we definitely did not make explicit use of that fact.
Yeah, so our proofs are more like there exists a transformer which will be able to approximate it, right? So we have not explicitly have a relation between what is the mixing time and how much my error will reduce and so on. So we don't have that kind of like exact like learnability or constructive proof about it.
Mm-hmm.
It's only an existential proof, as Guru was saying.
So kind of related to that, so you have your random mixing in addition to your deterministic window part and your deterministic parts. Are they constant? Are they shared both across training and across layers, or are they randomized?
Yeah. So across layers, we use different random partition, not even across layers, but even in transformer, there is this concept of heads. So this attention is not happening only individually. There are like multiple heads attending. So each head has a different random pattern. So the global and window is constant, but the random pattern is different across head and across layers. But once you pick it at the start, we freeze it. So it's not like every training step or every new inference is a different random pattern.
So what sort of kind of combined sparsity does that give? If you were to superimpose all of those random graphs, are you then getting somewhere close to having all of the connections present in your entire graph, or is it still very sparse relative to
It's very sparse, right? So you can assume so for example, assume the sequence length to be 8,000, and as I said, like in each row there is at most 512, right? So it immediately means you have like 1/16x sparsity, right? 1/16 of the entries only have a non-zero thing. Everything else is empty.
And Zheng asked, in fact, Madison and Zheng actually asked very relevant questions comparing the performance of BigBird with the kernel-based approach, which seemed to give some benefit over the linear approach, but doesn't quite make this level of sort of connectivity that we have here. So do you have an intuition as to why the kernel-based approach is performing less well?
Yeah. So one thing important to notice in this kernel-based method is how powerful your kernel is depends on how higher dimensions you usually map it, right? So if you think of these like exponential kernel or Gaussian kernels, which are characteristic, their actual phi functions are like infinite dimensional, right? But so suppose it maps it to a dimension r, then my total computation cost is something like r prime times, it maps it to r prime. So it's r prime times nd. Now, if r prime is bigger than n, then we don't get any benefit, right? It becomes quadratic again. So in their paper, what they do, they can't allow r prime to be very big. They just maybe make it twice the r or something like that. And so that somewhat restricts how powerful your kernel can be. And maybe that's why their performance is not as well.
Okay, thank you. So in kind of tying back onto this like sparsity idea, Ignacio Ayabachi asks that if you are fixing your total connections or your total number of connections, does that mean that a sufficient enough input will not have any random connections? If you have a sufficiently long input, that you will have to not have the random connections going on.
No. So, okay, let me explain. Maybe I was not very good in explaining. So how we do is we have this global, we have window. So window, so in particular, you can assume like each block here is one block in our mask, right? And one token, for example. So there is this input token on this side, output tokens on this side. In case of self-attention, they are the same. So say what's happening is we are saying in each row, so each input token will attend to 512. So now maybe you have two global tokens, so that's like two global here. In window you have three, so that's like 2 plus 3, 5 is given, and all the remaining 500 minus 3 or whatever numbers is all like random connections. So it's always, you will have this fixed number of random connection for each token, other than maybe the first two, which are the global ones. So other than that, every time it's the same number of attention. And that's why if you recall this implementation also, that's why I could pack everything in a dense matrix, because of the same shape and size, because the number of random per token is always same. So is the window, so is the global, and so on. So that's why everything is uniform shape, nicely can be packed in a dense tensor, and I can do dense tensor multiplications.
Thank you. So we've got a few minutes left. It would be great if we could go back and could you give a little bit more detail on your chromatid genetics example?
Yes.
We had a lot of interest in the chat about the genomic example.
Yeah, so I think so. I'll go over like the whole area of what we are doing. So what we do is like for this genomic task, I was saying like you first take like the human genome from the standard, like the benchmark genomic sequence across all 23 of our chromosomes, right? And based on that, you create like standard sentence piece kind of tokenization, do masking and so on. And we held out like the 23rd chromosome as our validation set to select all the good pre-training and so on. So we basically pre-trained on the first 22 chromosomes, and 23rd chromosome was held as a validation set for pre-training. Once you have this pre-trained model, now what's going on is there are these, so we didn't define these tasks. So promoter region prediction, like I'm not a biology expert, but there were a lot of papers which were doing these kind of things. And the main task of this promoter region is to find where the transcription initiation happens in the DNA fragment, right? And that's like a small segment of DNA. So usually what CNN promoter or this deep promoter was doing was looking at a window length of only like 100 base pairs or something like that, centered around the target region. Like you're saying, like given this target, is this a promoter or not? And you're looking plus minus 100 on each side. And they were getting an F1. So here we are reporting F1 score because accuracy is not very good, because most of the regions are not actually promoter, right? Most of the regions won't be promoter. So if you just report accuracy, just saying everything is not promoter will give you already 99. So that's why it's like a F1 score of saying whether it's a promoter or not. So that's the promoter region kind of task. In chromatin profile prediction, there are 3 different kinds of functional effects of different DNA fragments. So whether it's like a transcription factor, so it's a TF kind of identification, whether it's a histone marker, and I forgot what DHS was. But there's like some other functional effect of the DNA. And the task there was kind of, again, very similar, like given a range fragment of DNA, identify whether it's like is it a transcription factor or is it a histone marker and so on. And again, same, like most of it is not it's like an imbalanced data set. So you can't just report accuracy. So you report like standard people used to report area under the curve. So we also reported here area under the curve. And there was like something mentioned in this SVM paper about saying that these histone markers are, sorry, not in this, in the deep sea paper, that histone markers have a lot longer correlations needed to understand whether it's a histone marker or not. And in particular in that task, you can see like the gain is also much bigger when you're trying to encode like a longer sequence.
Okay, I think while there are many more great questions, we are at time. So I will pass over to Giuseppe to wrap up here.
Yep. Okay, thank you very much, Manzil and Sinead, for the excellent talk and discussion. And thank everyone in the audience for attending and for all the really good questions. So we will have another meetup in about a month's time. So looking forward to see you then. And take care. See you soon.
Thanks. Thank you.